Okay, welcome back again to the second lecture, and I better stop shouting because I've got a mic. Can we have a prolonged cheer from downstairs?
Concrete building.
Not getting a warm feeling about that, but I'll just assume that you can hear me anyway. And we'll go on to the second lecture, the last lecture before lunch, where we dive down into the nitty-gritty, as it were, and particularly dive down into the networking part of the problem.
Yeah, thank you very much. Okay, so this is more tutorial in nature. What I'll do is, if you can imagine, each of these little systems have a stack. So we've basically the metal, and then we've got the different components, the different layers of software above the metal. And what I'll do is I'll take you through some of those. What I won't take you through is the applications so much. I mean, I've kind of described some applications, but the stack itself below the application tends to be more or less of a similar nature. And there's certain options you can use, okay, depending on the application area. And then the application itself will always be tailored to whatever you want, okay? And this hopefully will give you a good feel of how these systems are built and composed, because they're not built, they're more composed. Okay, now I've entitled the second one, it's much more tutorial, I've entitled it the third wave. The reason I call it the third wave is a guy called Mark Weiser a long time ago, who unfortunately never lived to see this day, was predicting how things would change in computing. And he described the first wave, he worked for Xerox, and he described the first wave as where we had these big monster dinosaur computers, okay? That's still running banks, okay? And we have those big massive machines, these big servers. And then the second wave is where we started to move towards desktop machines and personal computers and home computers in the late 80s. And that was the second wave. And it changed how computing was. It revolutionized that part of computing. And now the third wave of computing is a combination of things. It's a notion of being able to embed the computer system into the environment. And in fact, it's described sometimes as the very opposite of virtual reality. Because virtual reality, you're trying to model the real world in a computer system with your headset and whatever. This is the opposite. This is where you push the computer into the real world. Okay? And the other aspect of it is this notion of tailoring, this notion of CAM computing, he described it as, where the computer serves you. You don't have to change your model of the world to suit the computer, which you would with VR. It changes its way of presenting itself to you based on what you're expecting. And see, we call that CAM computing. And this is the third wave, okay? So this is what I'll discuss today. Now, there's a lot of terms that come under this, and I just thought I'd just bandy some of them around to see if you get a feel for what's what. I hate all these terms. I absolutely despise all of them because it confuses people. But the old term that we used to use, and in fact, when I teach this in Imperial, it's called pervasive computing, or as I call it, perv computing. Anyway, then some people call it ubiquitous computing, and there's a whole set of conferences and research around the ubiquity of the machine. And that tends to take into account more of the human interaction. So it's a nuance, really. Then you've got the Internet of Things, which is more business terminology to indicate that these systems will talk to other systems on the Internet. So it's just a protocol difference, essentially. It's the same embedded system, but the comms is one that will ultimately communicate to the Internet, or directly communicate to the Internet, like your smart whatever fridge. Okay, then you've got M2M systems. I have yet to get a proper explanation of what an M2M system is. It's basically called a machine-to-machine. Okay, that's comms. That doesn't say anything about an application. But to be honest, most of my systems talk to each other, whether they're a wireless network or wireless sensor network or whether they're IoT or whatever you want to describe them. They tend to talk to each other. So I'm not too sure what M2M is, but you do see that particular term used. The oldest of all terms is embedded computing. It's shoved out into the space. And then the new term that the Germans use and the Americans use is cyber-physical systems. Now, they tend to mean all that of the above to mean cyber-physical systems. When I personally are talking about cyber-physical systems, I'm not talking so much about a computer system. I'm talking about the interaction of that computer system with the world. Okay? To me, cyber-physical systems means how that machine interacts with the world, and how that world impacts on the machine, and how that cycle continues. And so when I talk about a CPS or cyber-physical system, that's what I'm really talking about. I'm talking about systems of systems. One could be a physical system represented by, I don't know, equations or actual something else. And it also could be the digital system as well. So basically, I've put them up there because I interchange between them, just to let you know, because I hate all these terms, and to me, they're a small processor with a piece of wireless and some form of energy source, and they do something in a collaborative way. Oh, you're not going to see this slide in 100 years. The slides will be part of the video pack, so you'll see this in more detail. It shows the span of application areas that this subject can cover. Absolutely, you can tell by the density of that slide that there's an awful lot of opportunity in this field. And it spans from everything from, for example, the world of buildings, civil engineering and structural engineering, understanding what the behaviour of a bridge and when it's going to fall down and those kinds of things, how to make a building more efficient and so on. Discussed some examples about the world of energy in the last lecture, understanding how we can optimize this new wave of generating energy from crowdsource effectively ourselves, and so on. We've got all the home stuff, so you've got your Nest systems and all those kinds of systems, your smart fridges and all those kinds of systems. Some people are interested in them. Some people have, for example, I did have a smart home, and I've just got rid of it all. I got sick of it, breaking. And so on. So there's the smart home thing. Where it's starting to get very interesting is in healthcare. We're starting to see in healthcare things like, for example, remote surgery. We're starting to see how we can embed things into ourselves better. Signal processing for cochlear implants and so on is getting wonderful at the moment. And a lot of the challenges that I talk about in terms of communications and energy and so on, you see these challenges on the body as well, because we're basically wet. And I talked earlier about the field being very wet, and it's hard to get communications through wet effectively. And also, if you're talking, for example, about cochlear implants, you know, the signal processing is adaptable to how noisy it is. So if I had one in my head now and you're all nice and quiet, it wouldn't take up much of my battery. But if you were all to start talking, the signal processor would need to do an awful lot more maths, and it would suck up the battery. And so it's all exactly the same challenges that we have, but we're putting them in different places. Healthcare is very interesting right now, and actually in terms of the matter compiler and all the nano end of it, that's where that's all going initially. The other field I tend to work with is industrial. Some people call it manufacturing 4.0. Manufacturing 4.0 is where you start to basically build a robot out of your manufacturing plant. For many reasons. The most plain reason is to make it run faster, cheaper, better, but also to make it more adaptive. So as your product can change over time as demands change, which is one of the reasons, for example, like companies like Nokia did well early when they did, because they were an adaptable company and could change their production lines, though it hasn't really worked wholeheartedly. Transportation's a big one. A lot of people interested in the whole being able to make the transport, especially big cities, more fluid. To reduce fuel and let's say and air pollution and things like that. Retail is interested in tailoring and targeting people both in the space and online. And then we've got security, putting invisible boundaries around places, understanding where people are, monitoring people's behaviours, looking at their faces. There's a whole world of security there. And then just the networking itself, understanding how the computer networks and systems run. And we, for example, have our sensor systems in our computer rooms in Imperial to understand how the flow of air is happening in the computer room so that they can be more efficiently run. And also, sometimes people use the wireless sensor network as an alternative to the wired network in these machine rooms because there's just so much wires as well. So there's a whole plethora of areas, probably some more that I haven't even got on that screen. As this lecture is getting a bit sort of more tutorial, you can stop me if you like. Now, there's a sort of classical structure to how we set up these systems. Typically, what happens is we've got sets of services up in the cloud, and they may, for example, if you look at the organicity system, you might have a service that's looking at air pollution, or you might have a service that's looking at transport, and you've got all these different services, and these are at the application level. They might suck in data sets from different sources, so it might be some coming in from sensors, but other data sources, participatory sensing, or even more static sensing systems, for example. And anyway, you've got them bunched together to produce these services. So you typically have a service layer, a middleware layer bringing all this data together. And then down at the very bottom is our sensor arrays that typically build a network and talk to the the back-end cloud servers. And that's kind of the vanilla system that you'll see. You basically build your sensor network, you deploy it out, you'll have one or two what's called base stations, which is its link to the internet usually, and then that talks to these kinds of bigger cloud-based machines usually. That's very traditional. And at the moment, that's how, for example, most of the cities run. They run with all these sensor arrays at the bottom, and then they talk to these services up at the top. But let's just look at the sensor array. I don't talk about the cloud. You can do that in another subject. That's a whole subject of its own self. We're just looking at the sensor array and how to build one of those and how to get it to communicate back to the base station. And then we hand off at the base station, okay? So for example, in my whole research, I hand off at the base station, don't care what happens after that. So that's basically where my boundaries are. Now, we're drilling down, so this might start off sounding slightly patronizing, hopefully not too bad, but we'll start at the beginning. So the sources of data, basically we want to measure data, report them somewhere. Now our sources of data basically come from sensors of some sort. So you've got different sorts of sensors here. So for example, I've represented a sensor up here as a microphone. Oh, that's interesting, you can't see that. A microphone or some sort of video, for example, and this represents a temperature sensor. What you have to bear in mind, the type of sensor that you've got. The type of sensor kind of dictates how much power is needed to give the sensor some notion of power if it's required. Also, what the amount of data that's coming in from the sensor dictates how it's initially processed. So you're taking data from a sensor, you're pre-processing it, and then starting to understand it, and then probably sending it somewhere. Obviously, you can imagine a MEM-based, that is a tiny micro-based temperature sensor, doesn't use much energy. It's very lightweight in terms of what it reports, compared to a video-based sensor, which obviously is a lot more, there's a lot more data coming through from the video, or a microphone, which is sound. That's the sources of data. The sink of the data, though, is where you want the data to go. And then again, as I mentioned in the last lecture, there's a number of places. Typically, we send the data to a base station. So if we deploy something out in the park, for example, we have about 2 or 3 base stations in the park, and all the data is routed to those base stations. At the moment, it's a fixed base station, so each node knows where its own base station is, just to keep things simple. But sometimes you can have adaptive base stations where the system tries to maximize reliability by routing to a base station rather than a fixed one. Other sinks could be of mobile phone, and I showed where we suck up the data using mobile phones, etc. And then finally, the other aspect, the other component really is the actuator, something that changes or affects change. And that could be like, for example, an alarm, which I've got here, or it could be a valve on a water pipe network that opens the valve and lets more water through. There's lots of different things that could basically become an actuator. Other things that could become an actuator is where you've got a message on a phone. So for example, if I'm sucking in data and I've got some sort of weird thing happening, like a temperature, it's gone beyond, say, 30 degrees, that could indicate a fire. Maybe it's an alarm, but maybe it's a message on the phone to check that sensor. So the actuation can take many different forms. Oh, this is very small. So basically, let's look at this. So if we go stick to sensing itself, that is the acquisition of the data itself. We've basically got the basically, when we have a sensor, we look at signal processing. That's basically trying to filter the signal. What we have is analog to digital converters, which take the analog, if it's an analog sensor, and converts that into a digital format. Then we typically have a process of conditioning, where we condition the data that's coming in, and so on. So basically, this is the whole cycle. So we've got from sensor, conditioning, conversion, processing, and then we could have actuation at the other side. So effectively, it's like a set of components. Now, the signal processing algorithms that we use are typically pertaining to a given sensor, knowing what application requires it. So we're back to the idea of being able to tailor it. Also, it depends on what capacity the node itself has. So for example, we might have a hardware-based analog to digital converter, or we might have to do that in software. Software has the advantage of being more adaptable to change, so we can do things like live compression, but hardware is much more efficient in terms of speed and in terms of how much it sucks up energy. So effectively, we capture the phenomenon using the sensors themselves, and this could be the phenomenon of the world. So it could be a process or a system or a plant if, in fact, we're doing a control system. The signal conditioning basically takes the signals that come in from the sensor. It can amplify it. It can basically filter the data using standard filtering techniques, etc., to make reduce the data down or make the data make more sense. We can convert it from an analog signal to a digital signal, so it can be processed, and then it's often then sent at that point. Now, if it's sent at that point, it could be sent directly to an actuator to do something, or it could be sent up a network, and then the network makes a decision of whether or not to actuate. So we can have sensing and actuation both attached as a single cycle, or we can have a bigger cycle where the data is being sent up to the network itself. Now, the power supply, as I said before, is very important in these. We've got two types of power supply to the sensor itself. We have an active sensor that requires external power. In other words, they require their own power source. So, for example, it might use and it also typically emits energy to do its sensing function. And you can imagine then you would have different energy resources. Or you could have passive, where it detects energy and they basically get their power from that. For example, infrared sensors. So then you get an idea of what kind of sensor you have. Then you know whether or not you can afford, for example, to use solar panels, or you'd have to put a fairly heavy battery on the system. So, for example, when we're measuring soil, we have to put quite large lithium batteries in the pack. If you remember back the slides where I showed the composable matter, the first one you saw in a big grey ugly box was our soil sensors, yeah? And they take up so much power that we actually have, mostly in that box is the battery. The sensors themselves are about that size. They go into the soil. Nobody cares about that. But the actual processor and transceiver components are only about that size. In fact, you might be able to, I don't know if you can see these. So basically that size there. So that's the processor. The processor's tiny. Well, it's the processor and transceiver in this case. The box is mostly battery. Okay. So you have to understand, so normally what we do is we go to look for a sensor depending on what the application is. We look at the fidelity of the data that's coming in from those sensors. We look at the cost. As I said before, we term the under £100 sensors as lollipops because you know what you're getting there. It's not going to be super accurate, but it is super good value. Then the over £100 is what I call the mid-range. Those sensors are good enough, and we tend to use those a lot. So they're good enough for proper scientific study. So, for example, the soil science people will understand the data coming in and trust it, okay? And then you've got high fidelity sensors. Now, what's happening at the moment is the world of sensing is becoming very interesting. We're starting to see super low power sensors that are super high fidelity. So, for example, one of the sensor systems we use is called the token vibration sensor. It was designed by NEC Japan. And it basically has 10,000 samples a second vibration data, and yet it runs on next to no, it doesn't require much power. So it's a really lovely sensor to be used on lots and lots of things like, for example, civil engineering, things like bridges or pipes and things like that to understand the change in the environment. So we tend to buy the sensors based on what we need in terms of fidelity and our power sources that are available to us. So basically, as just in summary, that means we have to look at the accuracy, the statistical variance expected, and typically we get that information from the data sheets. Okay, so a company producing a sensor will have that information on their data sheets. They are not allowed to sell that sensor without having tested it in lab environments usually. And again, you have to take that with a pinch of salt. So they basically test it as into the degrees in which it will operate at high fidelity and where it will start to break up. So we get that usually from the data sheet. We have to understand how the system is calibrated. Does it need to be calibrated at the start of the deployment? That means you have to tweak the system to start reading as you would expect. And this sometimes means that, back to the notion of systems engineering, we typically hire super expensive sensors for a one-off deployment just to understand the phenomenon off the field, coming in from really super expensive sensors. Then when we put out our frugal systems, we can see what the difference is and we can calibrate depending on that. So we can start to see how our, not so lollipop, but even our mid-range sensors are starting to understand the same phenomenon effectively. So we have to understand calibration, we have to understand how it will drift and what causes drift. And as I said before, drift can happen because of the battery, the voltage going down, but it could also just happen due to time. The cost I've talked about a lot. Environmental factors, that they have basically a temperature range or humidity limits in which they will work accurately. So if, for example, if you take a sensor that works really nice in the UK and you bring it to a desert, it may not work so well in the desert, for example. Its range, some people don't take this into account. They forget that the actual accurate range in which the sensor is supposed to work will not give you information beyond that range. So if you're not too sure of the phenomena you're trying to understand, this is where we have that weird cycle again and again, where we didn't realize the sensing range should have been broader than our sensors that we bought, so we have to go around the cycle with more expensive sensors sometimes as well. Repeatability, obviously, the variance in the sensor's readings is very important, and a lot of the times we don't just trust a single reading. We take in readings and we start to look at trends, again, just assuming that everything is not going to be perfect. We look at trends, we look at averages, and so on and so forth. And again, the resolution, that is like, for example, numbers of samples a second, the fidelity of the sensor's ability to record the phenomenon. So, for example, you typically want to record the phenomenon at twice the rate that it happens, okay? So if you're talking about video, you're basically recording at twice the rate, so you are sure to pick up the phenomenon, okay? So that's the usual thing we do. Sorry about this slide. So this is a bunch of sensors. These sensors are, to give you an example of the type of sensor, we've got temperature, pressure, optical, acoustic, mechanical, motion or vibration, position, electromagnetic, chemical, humidity, and radiation. And then the examples are down here. So for example, for acoustic, you've got piezoelectric resonators, microphones. For pressure, you've got gauges, barometers, ionization gauges. For chemical pH sensors, we use that a lot in precision farming. Electrochemical sensors, and infrared gas sensors. And so the sensors themselves start to get a bit bulky as well. Humidity, you can get little nice MEMS-based systems. MEMS-based systems are basically sensors on a chip, effectively. Super lightweight, super low energy consumption, really nice. And a lot of the systems that we typically use with our students have lots of MEMS sensors on them. So for example, this one I think it's got about 5 sensors on it, as well as a processor and transceiver for radio. And they all cost 20 quid, so it's nice and cheap as well. Yeah, so this is an example of the sorts of kinds of sensors that can retrieve the following information. And you choose the one depending on the phenomena you're trying to measure. And then, as I say, your rule of thumb is to double the sensing rate, the numbers of samples per unit time. Okay. Now what we've got here is basically, you can imagine you've got analysis, storage, mining and processing of data, and you've got the data coming in from these different sensors. We typically use multiple sensors, usually hundreds or thousands depending on the environment, and they typically form a network. The structure of that network also depends on the application. So for example, you can have this multi-hopped based network where you're allowing the data to hop across a big space, for example, if you're not requiring certain delays to be exact and predictable. If you know, for example, if you're running a control system where the delay is very important, you would not run it, you would not have that structure. What you would have is a more star topology, where you have a single base station and everything is one hop away, okay? And then you can tell each one of those nodes when to run, and we'll talk about that later. So the topology of the network pertains to the application and its requirements, and also the environment in which the system is placed. And typically they work cooperatively. That's the main thing. You have to remember, each of those nodes are dumb. They're fairly low-end computing. They're dumb. It's the collective that's the intelligence. It's the system that's the intelligence. And sometimes they can monitor quite complex environments, therefore. Then this is wirelessly communicated to a base station, or many base stations, as I talked about earlier, and then that propagates the information for storage, analysis, and processing, depending again on the application. What we're starting to see in terms of trends in this end of computing is to move a lot of this processing out to the network itself. And this does 2 things. It means it reduces the amount of communications, which ultimately lengthens the lifetime of the sensor nodes themselves. And it also reduces the complexity back at the back end, because if a system's got so much data coming in, can you imagine 10,000 samples a second being relayed to a cloud server for processing? That's unbelievably complex, especially if you want to cross-correlate that with some other data. So that's very complex. So it's nice to be able to just reduce that at the edge, therefore saving bandwidth and energy for transmission, but also complexity of processing at the back end. Now, to do this, we have a number of challenges. The first challenge we're going to talk about today is energy, because this has kind of been the Achilles heel for so long. Now, they're typically powered through batteries, and they're replaced when the battery's depleted. I'll give you an example. So the Victoria and Albert Museum in London, the Science Museum in London, and the Natural History Museum run an 800-node network. What they do is they've been running it now for 10 years, and what they have is a bod, a human being, who basically takes 40 nodes down a month, takes them and replaces them. And when they take them down, they recalibrate the sensors. It's just humidity and temperature. Recalibrate the sensors and replace the batteries. That is that person's job. 40 nodes a month. So that's what they do. They basically do that cycle every month. And therefore the system, and they haven't changed that system in the last 10 years. So basically, this is what happens in reality. So somebody looks after the system and replaces the battery when it's depleted. Some more sophisticated systems report batteries being depleted, but then every time you report something about the system, you're communicating. You're using that very system that you want to have longevity. Some of them have rechargeable, notions of rechargeable, for example, solar panels on them, and usually they're typically outdoor systems in the UK or indoor outdoor systems in some places as well. And some people just design the sensor node itself to be discarded once it's been completed. So it's just throwaway sensors. Again, you have to take cost and environmental issues into account. And even with the batteries here, you also have to take environmental issues into account. Now, the thing is, you have to be able to calculate in advance what you think the lifetime of that system would be as a complete system, taking into account its operation, the amount of communications, even in an environment that is changeable. Okay? And you have to be able to predict how long your system will live to give an idea of its mission time, because this is what the user wants. They want to know what the mission time of that is. And it's not very easy to do that. Typically, we use these back of the envelope calculations to give an estimate, but we don't know for sure, for example, if a bus drives in front of one sensor node, and basically it means all its data is routed round along set of links, and that starts to deplete all those nodes as well. We won't be able to predict that bus sitting in front of that node at all. So, for example, we have those kinds of things that we can't predict so well. So there's a lot of things that impact on the energy. The physical layer, i.e. the hardware itself, that is the processor, sensor communications, obviously consume the energy, so therefore we have a notion of how much that costs. Again, we're back to data sheets for this. Data sheets are usually given out with the nodes themselves. You look at the data sheet, you look at the different components of the node itself, and then you can see where the energy is being spent. For example, the processor might have different modes. It might have active mode, and it might have sleeping mode, and these different modes consume different energy levels. Then you've got the MAC. We're starting to go up the layers now. So the next thing, you've got the physical layer. Then you've got the medium access control layer. And we'll talk about this in much more detail later. The medium access control layer is basically where the communications hardware wants to get access to the air. Simple as that, the medium. And to do that, it's got different ways it can do that, and we'll cover that later. And it costs. So for example, if you've got what's called a contention-based strategy, it's quite energy costly. So a contention-based strategy is basically, can I use the air to send a signal right now? No, back off. Can I use the air to send a signal back up now? And basically, if it starts using the air before it's allowed to, it can collide with other communications at the same time. And therefore, then it loses that, the packets don't get transferred, and it has to start again. And then we have to somehow account for that in our energy calculations. And the other thing is, if you're communicating to another node, that other node has to hear it, okay? Now, it costs, this is the thing people don't realize, it costs obviously to send a message, but people don't realize it costs to listen to one as well. And in some systems, in some transceiver systems, it's even more expensive. Now, I understand that in terms of electrical, but it's even more expensive to receive. And so if I'm if I'm part of a route, say for example, that's been established, I'll be waiting for those messages coming in. I can't go to sleep. I have to have my transceiver up and ready to go to receive that. And that costs me, even though I'm doing nothing right now. So we have to take that into account. That's idle listening. Okay? Now some systems have modes that allow for low power idle listening, where it stays down in low power until it feels a chirp, right? And then it goes, whoops, better get into high power to listen to what's actually about to come in. Okay? So there's two modes, two levels, a kind of half asleep, where you're just sort of half listening, and then you go into full mode, and then it starts to cost. Then we've got the network layer. And obviously the network layer, have I got a bug? The network layer is responsible for finding energy efficient ways of getting the data across the space to where it's supposed to go. And there's a plethora of different ways of doing that. I will show a couple of versions of that later on. And then the operating system itself. Typically, the operating system is a non-operating system. It's a runtime, super small memory footprint, and it has to have efficient task switching. So very, very basic systems don't have much of an operating system. Basically, the tasks are scheduled as they arrive, and they just run in order. That's it, simple as. That's okay for a lot of systems. A lot of systems aren't very complicated. They're basically sensing, processing the signal. You know, it's a pipeline. Processing the signal, sending on. Nothing much else. So you basically do that in a loop. So that's quite simple. So you don't need a sophisticated operating system for that. However, the trend is to build more into these systems at low power, and therefore they're starting to get more sophisticated. So we're starting to need all the sophistication we have in our phones and other systems, and have a proper scheduler and so on. And in fact, all the Intel kit basically runs a light version of Linux, and it does have a Linux scheduler on it. And then obviously security. Security costs. Now you can have some algorithms that are fast and simple for example, encryption, authentication and so on, but they cost, they're running there, they're not for free. What we're also starting to see is that's being built in hardware. Encryption is being built into hardware. And we're starting to see that because it's so important that these systems are secure, that they've put that into hardware, therefore it saves energy and has a decent level of speed. But to be honest, most of these systems that are put out are not at all secure. And then there might be some notion of middleware to coordinate these systems, to allow these systems to do some job together. And this allows them to do, for example, in-network processing, where the actual system itself doesn't report to a base station directly. It collaborates to understand something first, makes a decision, and then might do some sort of, I don't know, aggregation of a reading or an actuation. Now, when we place these systems in the space, the actual shape of the space, let's say, dictates a lot of how the system will run. And we want these systems to have a notion of the ability to, you know, adapt and change while they're running. So we don't have someone constantly out trying to maintain them. So we typically see a lot of the time what's described as ad hoc deployment. That is where they're deployed without design. Now, I'm seeing this less and less. Now, I think when the subjects started 10, 15, 20 years ago, people thought we could just sprinkle them out of an airplane and they would just land and form a network and that's that. Maybe in defence applications, yes, right? But what we're seeing now is much more the need for design, because we need to understand the environment that we're sucking in data from. So for example, as I said before, it's really only battlefield type assessments that we need to have no design in terms of placement. Usually they're placed where they're needed, for example, tracking patients people in a disaster zone. Or we might have a notion of a moving sensor system where we've got robot teams and so on. So the placement is very important because it has to understand the phenomenon, and again you have to take all those communications and so on into account. I'll give you an example of where we're playing with that at the moment. We've got a big drone system that put out little tiny drones, well not drones, UAVs. And the tiny drones basically latch onto walls as tiny sensor systems, but the big drone system basically sets them where it's worked out mathematically the best place to set these. And we do this with Aero. And then they latch onto the wall. They've got this lovely little mechanism that latches onto the wall. And then when the environment or whatever changes, the big drone system can send a message to pick up those again and send them elsewhere, you know, to have them attach elsewhere, because the placement is actually so important in this particular application that we're talking about. So you can have, you know, a mixture of systems planting them and human planting them as well. A lot of the time, the sensor must have an idea of where it is in terms of its location. It doesn't have to be super accurate for certain applications, but it might have to be for certain other applications. So, for example, some scientific applications, it needs to report where it is so that we understand the phenomena is coming in from that place in a city or in a field or wherever. It needs to be able to understand who its neighbouring nodes are. As I talked about earlier, one of the mechanisms that we use throughout this subject is to understand just our neighbourhood, because that's a good, cheap way of understanding the network as a whole, and then from that make a decision based on what I see in my local neighbourhood, my one hop distance away. And then from that I make my decision of what I'm going to do that ripples out across the network. So we need to know who those neighbouring nodes are, and there's different mechanisms of deciding who they are. We need to be able to configure the parameters of that node. For example, if I want the sample rate of the whole network to be 10 samples a second, and then I start to see that I'm not getting interesting data, I want to be able to send out an update to that, and that's non-trivial as well. We need to be able to discover routes to the base station where it's not a star topology, and initiate sensing responsibility. That last one could be in a situation where we know that the sensor placement is such that there's a level of redundancy in the sensing. I'll give you an example. On a water network where you've got, say, one single pipe and you've got 3 sensors along that pipe, you might find that, okay, maybe it's a multi-kilometre pipe, but because of the nature of water and it ripples along that pipe, we can work out using one sensor how that ripple has happened, right? So we can turn off maybe 2 sensors and just have one on at a time, or put them on when maybe some weird phenomenon has happened. So we can use this redundancy, and understanding that is one of those cycles where you need to understand the phenomena to be able to know when to reduce the sensing, but you need to sense to understand the phenomena in the first place. So it's one of those funny cycles. Now there's lots of, so energy was one thing. Now the wireless network itself, as I'm constantly saying, brings with it a lot of challenges. The first one is attenuation. And that basically is where the signal dies off, off after a different distance, essentially. So it's basically, imagine a wave that starts to deplete. And this limits the radio range. Basically that's even in an open space like a football field, for example. So that attenuation impacts on how we design the network. In other words, if we've got a highly attenuated network, maybe even in rain it attenuates more, we might want to have this notion of multi-hop communication. Now what it has is the advantage of being able to jump the message across all the different nodes, which increases the reliability of it being transmitted, but it increases also the latency. Because every time that message is hopped to a neighbour, it has to go into the neighbour's incoming transceiver, be processed a little bit, doesn't have to go up to the application layer, it's processed down at the radio communications level, and then it's sent on, okay? So it's cheap in the sense that you don't have to look at it from an application perspective, you don't have to pull it up the stack, it just gets transferred on. Because I'm not interested in it, it's not my data. So, but it does increase latency because it has that little interaction. It also can increase failure because you've got more components in the mix now. Once you have more components in the mix, the probability of failure is higher. And it's also complicated by the use of duty cycles. Now, had we not been in a 2-room environment, I would ask you that question. Why is the duty cycle a problem here? Firstly, what is a duty cycle? The duty cycle is basically our way of telling the node to go to sleep. Now, there's 2 components to this. I can have the radio turned off because it's expensive to sit and listen, and I turn it off and on periodically depending on what I want to send, okay? So I turn it off and on, and that's the radio duty cycling. Or if I'm not needing to measure phenomenon at a time, I can turn the whole node off. I can turn it all down to low power, nothing, turn it completely off in some cases. And then we save that period of time in terms of communications power and processing power and so on. And therefore we lengthen the lifetime of the actual system. And we call this duty cycling. So this cycle of turning off and on the node is the duty cycling. Now if we've got multi-hop communication, and I know that my phenomenon comes maybe every 5 minutes, I know to wake up just before that time and start sensing, and then I want to send. But if my node beside me, or one down the way, does not have that same phenomenon pattern, it might be slightly different, and so it goes to sleep at different times for me. I can't hop to it because it's asleep, and I have to somehow schedule that. So this is why multi-hop communication is very good, very reliable, relatively. More complicated to program, but it has other problems as well. Latency, error probability, and you have to schedule the nodes to be awake to form a route at the same time. There are other challenges. So for example, if we decide to centralize our processing or decentralize our processing. Now there's different trade-offs here. So for example, if we have a notion of centralized management of the whole network, that means there's a computer setting saying, right, this network will be more optimal if it forms this shape, if the routes are here and this is how it's going to work. That way you will more likely to get a genuinely optimal situation. The downside of that is, though, for it to be able to make, the base station to be able to make that decision, it needs the data about the network, right? Not the data from the sensors, it needs that as well, obviously, but it needs all this metadata, all this housekeeping data about the network. So what it does is it's basically saying, right, I need to know from all the nodes in the system, I need to know what the battery levels are, I need to know how fast you're using up your battery, I need to know what your links are between each other. So that's every combination of every node in the whole network. So you can all do the maths for an n node network. You can imagine how many communication links possible there, depending on the space. So it needs to know that. It doesn't need to know it in a moment of time, it needs to know it over time, so it needs to know more than one sample of that, and so on, for it to make its optimal decision. Now, if that data is being sent in by the network, that's very expensive, because that's the same as sending in your original sensor data. And you have to remember these are frugal systems. Typically the data rates are slow, typically you can't send massive giant packets of data, so it's not like you could piggyback that information constantly on the main data coming in from the sensors, which is the obvious first step that you would do. So you do have, it costs. So you have to take the trade-off of having a completely optimal system versus the cost that it will to get that data in to do that optimization. The second part of that is the dynamics of the environment and the fact that this changes how the system works. So for example, two nodes that could talk to each other, a bus drives in between them, they can no longer talk to each other. Now, if I'm periodically getting my housekeeping data back to do my optimization, I could miss that bus part. So at that moment in time, that node is trying to talk to the one across the bus and can't, because it's a very inflexible system. It knows its best route is to talk to number 2 node, which is across the bus. So that's not going to work. So it's not very tolerant to sudden failures or sudden changes in structure of the network itself. So we've moved away a lot from this decentralized notion of sending in housekeeping data and making it optimal. We've now tolerated suboptimal solutions, best effort-based solutions, where, as I say, if we understand just our neighbourhood, we can make good decisions at that level. That means the network is reasonably decent in terms of performance across the whole network. And this is much cheaper because you're only having to know your neighbourhood, and your neighbourhood's one hop. It could be just a small number of nodes. Okay. Now, there's different applications then dictate how we do this communication. So we've got these different interaction patterns, and this is between the sources of the data and how they're sent to their ultimate sync node. So the one type of application that we have is called event detection. And this is basically where you have a situation that you want to monitor that happens on a given event. So it could be a predictable event, or it could be a non-predictable event. And you have to be able to schedule the system to wake up and sleep based on that, to have enough power either to live through that and so on. So you've got the whole computer system has to understand how best to not miss that event if you want to optimize the situation. Then you have got periodic measurement, which is very typical of utility-based systems, where you're periodically keeping an eye on the flow of water through a network and so on. And that's just periodic. It's because it's predictable almost. The phenomenon itself is predictable. You know what you can do. You know when you can go to sleep. You can schedule your system. It's an awful lot easier sensing application. Other systems try to do some notion of function approximation. That's where you want to not necessarily grab the data and send it back for processing. You want to try and understand the nature of the space. So you can actually do more edge processing or in-network processing of that. For example, you might want to just understand where the temperature is 30 degrees, right? And you just want to say, within these geographical bounds, the temperature is 30 degrees. That's all you want to send back from your network. You're not sending all the data back. You're just saying to your neighbours, trying to work out in the network itself, where the boundary of that, say, temperature range is. And then one node is elected to send that back to the base station, that it's within this boundary, this geographical boundary. And the same that with edge detection, you're wanting to understand where things change. You're trying to build a map, effectively, of the area, not sending all the data back. And the last one is, the last type of system is a tracking-based system. And that's where you've got a field full of sensors and something is moving between them, okay? And so the easiest option is to have all sensors up and wake, and then they watch, say, what we call the pink elephant running through the space. Or you could have them scheduled that they do things like tricks, like, for example, all the nodes are asleep until one of them says, right, I'm detecting an elephant, and it sends out a low-powered chirp to all the half-awake nodes, and then they start to wake up. But the node is understanding the trajectory of the elephant through the space, and it starts just waking up the nodes that are on that trajectory. So there's nice, clever ways of doing that. So, for example, if I was going across the diagonal of a room, all the nodes at the far sides don't need to wake up, just those in the middle that the elephant's more likely to be walking through. So there's all these nice tricks to maximize the lifetime of the nodes themselves. So we talked about deployment before, and we've talked about mobile sensors before, so I'll just skip this slide, actually. And the other side of this is maintenance. We take into account when we're designing these systems how on earth we're going to have them live over time. And obviously maintenance is a very important thing, because if we've got to maintain them, we all have to build software to do that. And and software that has to do the maintenance is interesting, because it's the opposite of sensing. Because sensing is basically taking data from the area, filtering it a bit, and then sending it to base station. Maintenance tends to be coming in the other direction. And a lot of the radios that have been designed traditionally are good at sending the data up to the base station, but not so good at sending it down. So we have to take that into account. And again, as I said, the energy is a big deal. So let's look at the stack itself. So we've got the stack itself, if you maybe can see this. You've basically, as I said, at the bottom, you've got the hardware. You've got your clock. You've got your A to D as your analog digital converter. You've got your interfaces to your sensors, I2C or whatever, okay? And then the next level up is your transceiver, effectively. And you've got your transceivers here, in the hardware. And then you've got your MAC layer. As I said, the MAC, very briefly, is where it's trying to get access to the medium, mostly air. And then it produces packets, which are then produced to the routing layer. And then the routing layer sends that up to the application. The application layer, the thickness of that depends on how much in-network processing goes on in the actual node itself. So that's typically the layer. So what we look at today is the MAC and the routing layer, so to give you an idea of what options you can have. Just to be more precise, the typical major components, as I've been talking about them, but I probably haven't shown you a picture yet, is we have the transceiver, which does all the radios. We've got our sensors, which sends the data into the converters from analog to digital. Microcontroller does the processing, and we could have some sort of bits and pieces of memory. The memory is usually tiny in these systems. Some of them could be 4K even. And then we've got our power source itself. And as I said before, it's usually batteries, but some of the time it can be solar panels or some sort of piezoelectric vibration sensor that produces energy. And so this manifests itself to look like this. So we've got our energy supplies, could be from anything. So we've got like an example of vibration here. We've even got wireless energy transfer. There's a lot of work at the moment looking at how you can take ambient energy in from the environment. So for example, from the wires that are running around the room, you could get some notion of the energy from that transferred into your system. And it's a bit like the transfer of energy for your smart cars and so on. That you sit around on a plate. There's a lot of work now looking at induction, for example, where you just have a coil in the wall, or a coil is actually the frame of a picture, and you could power up your sensors in the environment based on this picture frame that's through induction is giving energy to the system. So this is a nice, interesting area to look out for, where we don't even need solar panels or other sources of energy. We can actually take it from the environment or even from Wi-Fi. Storage is important. So for example, if you've got a normal battery, you've got all the problems with the battery, but even if you've got a renewable energy source, you have to look at the buffer, as it's called, or well, sometimes even call the battery in that. And these, as you know from your mobile phones, only last so long. As you know, you recharge and recharge and recharge a mobile phone. In 3 years' time, it's pretty much depleted. Now, in terms of us calculating that mission time, we have to understand how long these will be efficient for, and we have to take into account that they have a notion of where they lose the energy, even though they're fully powered. And then we have, as I said before, the energy consuming parts as well. You've got controller, sensors, transceiver, and so on. Just to give you some examples of, for example, the costs, these are all different. This is one microcontroller, and it's got different states. I mentioned this before. It's basically got active mode, where it's consuming up 1.5 megawatts, but it's got different low powered 0 to low powered 4. And now you're talking it's milliwatts, 1.5 milliwatts in active, and then you're now talking microwatt levels for the low powered modes. So it's got different modes, and you can program the system to go into these different modes depending on your application to maximize the use of energy. The radios, as you can see here, so this is the CC2420 radio, one that's used a lot in the systems that we play with. It's got different modes as well. So its sleep mode is 0.1 milliwatt, and its active, receive, and listen mode is 59.1. So you can see all of that is what we need to understand how we can lengthen the lifetime of the system. And then the sensor board itself on its own, not even the sensor board can consume energy for reading, writing, and erasing as well, if you have that. So you can get an idea of that was just ballpark figures. So, So what we tend to do, as I said before, we kind of give a back of the envelope sort of style calculation to roughly understand the cost. There's no point in going into super details. So for example, in this tiny example I've got here, if we use this very rough figure of where the lifetime of a system is the capacity of the battery divided by the power consumption, and we have two batteries, that basically the power consumption is 62 milliwatts, and the CC2420 radio is always in that state, then we can work out what the lifetime would be. And it's very simply, it would be 5.6 days only. So you've basically got what that would be a Berkeley moat, two batteries, very typical configuration. You send it out and you only have 5.6 days operational time. That's not worth the effort of setting something out into space. So what we do is then we turn off the system a fraction of the time and save. And this is an example of different duty cycles here running. So that's 10% duty cycle, 50%. And some systems can tolerate very high duty cycles, or very low duty cycling, sorry, where the system is turned off a lot of the time. So in this particular calculation, we get a serious amount. If we have a 10% duty cycle, we can get 50 days out of it, and so on and so forth. Still not brilliant, obviously, but we're getting there. So that just gives you a sort of percentage understanding of how you need to understand all these different components and how much they will impact the system. Now, if we want to look at how the energy for a transceiver works, and I'm just sort of skirting through this, to be honest, you can see how it's actually more complicated in reality. So, for example, if you're talking about transmission for a number of bits, you basically have the amplifier power, which is a notion of the basically the irradiated power coming out of the antenna itself, and it depends on the model and obviously the efficiency of the actual system itself. Then you add the transmitter electronics itself, which obviously requires power, and then over time, so the time to send those bits across the medium. And that depends on things like, for example, the encoding rate, the probability of error, whether it has to resend, and so on. The other thing we have to take into account, the fact that if we've been duty cycling the transmitter or the transceiver, it has to leave sleep mode, and that is not instantaneous. So you have to also account for the fact the system has to wake up and then start its job. Okay, so you have to account for that as well. So you can see beneath the hood it starts to get slightly more complicated, but not too bad. You can still do rough calculations. And so things that we're not considering in this, even though is, for example, distance. We're not saying about whether we're upping the power to make it go further in terms of distance, and we're not even calculating routing, where you're relaying data through other nodes. So we haven't even calculated that, so we have to add that on. Receiver's pretty much a reflection of that. Again, the receiver has to wake up we have to take into account the receiver electronics and the radiation coming, from the antenna coming in. Now, duty cycling is not free in its own right. Let's look at the diagram. So, for example, the typical thing would be if you had an ideal world, you'd greedily switch into low-powered mode when possible. In other words, I've read the phenomena that's interesting right now. I think I'll just go to sleep, okay? But you can't really just do that because the time and power consumption required to switch is not negligible. It introduces an overhead, which you can see here, and only pays off if the time saved is greater than that overhead. So, for example, here's an example of event-triggered wake-up from sleep mode. You basically have the power consumed while asleep, the power consumed while active. It's basically going into sleep mode. It's not instantaneous, so all this is used up. So there's a cost, a waste there, that you can't do anything. You're sleeping, okay, you've got a saving here, but then you're costing to come back up again. So you have to balance that out. So typically, if the phenomenon that you're recording is in terms of time distance between it, you're not going to keep putting the node to sleep and waking it up again, because that is just wasted power effectively. The other issue with going to sleep and duty cycling your system is that, it should be synchronized, and I mentioned this before. So we've got one node that just wakes up and goes to sleep when it suits it. In other words, whatever it's measuring, it suits that cycle. And we have another node that's waking up and go to sleep. And you can see they're not synchronized with each other. And that means that this node has woken up, recorded its sensing data, and then gone to send it wants to send it, but it's gone to sleep. This node has woken up and it wants to send it to maybe node A to relay it across the network, and it can't because this node is asleep. So you have to schedule that somehow. And then to do that, it costs. To schedule these systems costs. You don't get that for free, because that means that all the system in the area has to understand what the notion of the same slot of time is, so that they all agree to wake up and be alive for that moment in time, even though it may not suit their sensing schedule. The other thing that you have to take into account is clock drift. We're down at the low end of computing, and the low end of computing means the oscillators, the clocks on the actual processors are pretty rubbish, which means they start to drift. And in some cases that can be a few seconds per day, depending on how cheap your machine is, effectively. So if that's 2 or 3 seconds a day, 2 or 3 seconds in terms of duty cycling can make a difference. It can make the difference in that it could disrupt your routes, and you're constantly having to route where it's not necessarily the best route through the network, it's just the one that happens to be awake while you're awake. Because the actual processors think they're waking up every 3 seconds, and they're not, they're asleep, because of clock drift. And clock drift was a massive problem. In fact, was one of the contributors to the lack of synchrony that we saw on the Christmas tree diagram earlier as well. And this brings great challenges, as I said, both for the notion of the medium access layer, and obviously agreeing to route data across the space. That's just a slide showing all the different times to go to sleep and awake. Again, I think it's too small for me to convey it to you, but you'll see it in the slides when I give the slides over later. So let's go into communications more. When the slide decides to, that is. Oh, there we are. Right, so we've got different ways of doing it. We've got single hop routes and multi-hop routes. We've talked about that a fair bit. Now, the main reason we tend to use multi-hop is to kind of extend the range of the wireless communication. As I said before, if you want to shout louder, you can use more power, fine. But if you shout louder, everybody else can hear you. It means you're interfering with them as well, okay? Which means if you're interfering with them because you've shouted louder, it means, well, they have to back off. They have to go, either I'm not going to talk, or I am going to talk, but the person I'm talking to cannot hear me, and I'm going to have to say it again. Okay, so the power of me shouting is not a good thing, because it hurts you and it hurts me. Okay, so we want to reduce any, upping the power of the radio communications as much as possible, and we want to limit that to a certain degree, and that's why we tend to use multi-hop systems. The other thing is to do with, what's the first one was transmission power. The second one is to do with path loss and obstacles, where you just actually physically can't get the data or the transmission through something. Thick concrete, these buildings are a nightmare. Thick concrete is a bit of a nightmare. Anything with metal in it, anything with water in it, nightmare. So basically, you've got an issue with path loss and, as I said before, obstacles. So typically, we will use multi-hop networks at the moment, and I'll talk later about other networks. And this is where you basically relay the data through an intermediate node, and it forwards the packet, and this is called a store and forward network, pretty much like TCP. And so, for example, the source is here and the sink is there. You can't go through the mountain, so you have to go round the mountain to send the data. So basically, we can do this using, for example, collaborative networking or network coding to make that much more efficient. I'll not cover that today, but it is slightly more mathematical, where you can basically exploit the nature of the wireless network to make sure that the data is more efficient and lightweight and more reliably sent. And it tends not to operate on a per packet basis. Now, the obvious idea is that if we multi-hop the message through all different nodes as relays, then it should be more energy efficient because I'm lowering the power of the transmission, the antenna's transmission. But we have to take into account the path loss component. That is the reduction in power versus the attenuation. The attenuation is the drop-off of the signal. Here's an example. So we've got basically power versus distance. And you can see there's the power. As the power starts to drop off when the distance. So this is the attenuation, essentially, of the signal. Okay? So you can see what the problem is. As the distance goes further, we don't have the power to be able to receive the data. This is an example just to show us running the exact same thing, where we've got the theory that we saw before, and this is a real antenna, just to show you it's not all nice and clean. So let's look at this. So for example, if we want to send a piece of data from N to receive, so N send to N receive, and we've got a relay node that we know is here, we can send it with probability of 0.8 over that distance and that again. So our probability of success is 0.64, but we improve it if, the probability of error actually, and we basically improve the probability of success if we send it using the multi-hop version. What we do is we take into account, for example, that the energy we reduce from basically what would be the path loss coefficient. That is, the path loss coefficient of error has already been measured, we know that. And because we're dividing the distance by 2, therefore we save our energy. And the path loss coefficient of a medium is different for each medium. So 2 is for air. That's been measured by loads of scientists. But if you were to do it through, for example, water or through soil or other mediums, that path loss coefficient changes and changes this equation. We also have to take into account all sorts of surfaces that exist. So, for example, pointy surfaces, walls, and so on can make that become much more lossy. And hopefully you'll see that in the next slide. Right, it's okay. Right. So this is where we can see the distortions. So the wireless transmission can be distorted by the environment, this linked with the physicality again. So we've got different sources of distortion. The first one is attenuation that I've already mentioned, which is where the energy starts to deplete as over distance. Then we have other things like, for example, reflection or refraction, where the energy signal can bounce off a surface, and it can also bounce and enter the material of the surface. So, for example, when we did our underground network, we actually used the surface, the fact that it could bounce off the surface, to increase our ability to get the radio communications to happen. So we can actually exploit that. And there was a study in, I think it was Berkeley or Harvard, where they put mirrors on the roof of their machine room to bounce radio signals across the machine room because it was much more reliable and much more efficient. So they actually put a mirror up to bounce it literally across. Diffraction is another one where you've got some sort of sharp area that creates a new wave. So you've got a nice strong signal coming in here, and a sharpness can split that wave up, and now we've got 2 weaker waves coming out the other side. We can have scattering where we've got multiple reflections off a surface, a higgledy-piggledy surface like this, where the nice strong signal has come in, but it's bounced off and reduced. And there's other things like a shift in frequencies causing Doppler fading and so on. Now, we know these things happen, and so we can tune the system to kind of operate. Once we've got it in its space, tune it to operate knowing these things. And as I said before, we can exploit it in some cases, like we did in the underground. We wanted it to bounce back off the actual surface of the underground to go back in again. So you can actually exploit these. But these you have to take into account. And so, for example, if you've got a transmission and receiving device, you basically have the line of sight path where the transmitter is sending a signal to the receiver, and that's the line of sight path. But also that same signal, especially if you're using an omnidirectional antenna, will also send that signal up to maybe a wall and bounce that down again. So your receiving electronics has to take account that it's got a signal in here and a slightly delayed signal coming in here, and they're the same signal. And so it has to take that into account. And when that gets much more complicated, we find that we're dropping lots of packets, and then we have to do resend where that type of application exists. So we have to watch that. And if we're moving in the space, then we've got this notion of fast fading as well, because we're moving through the space as well, and that's changing dynamically. So this is a quite physical example. This is from Berlin. So here what we're seeing is a nice example of a physical space where we've got objects in a space. The brighter the colour, the stronger the signal. This is obviously quite a simple fact, but if you can see their shadows. You can see how it's changing the signal here. You can actually physically see the signal, which I think is very interesting, to really bring home some of those ideas. That's an outdoor space. An indoor space is this example here where there's our source, that's basically our antenna source, and the receivers are all around the building. And you start to see lovely signal along here, obviously the neighbour areas. It's almost like a light, literally. And then you start to see these dark areas. My office in Imperial, by the way, is a dark area. I can get no radio communications in it at all. And I think it's on my filing cabinets or something. But anyway, you can see that this, due to distance, but also actually there may be some sort of other obstacles around here, thicker walls or whatever, and that signal can't get to that corner. But you can sort of get an idea of where that one signal is going based on the colours in this diagram. And then this is the city signal, is the Wi-Fi signal in Berlin. You can see there, the source of it, the radio is here. And you can see, look at this lovely big dark space here. And that could be caused by buildings or, like skyscrapers and so on. Or you can exploit the skyscraper to bounce the signal off as well. So there's lots of tricks to do. But this is what we have to take into account when we're deploying these in reality. So that we can maximise the signal to the space. And if we can't, then we have to put relays in to be able to overcome that problem. So noise is one thing, all these problems, but interference is another. And interference, I've been told today, was one of the reasons that we weren't working in terms of our microphones. That is where if I'm chirping out at a given channel, on a different channel, and someone else is also using that channel who's close to me. I'll give you an example. So we were doing earlier versions of our underground stuff above ground first. And it happened to be interfering with and being interfered with by our security systems, the walkie-talkies from the security guys. And so we were not getting the packets, and they were all getting all sorts of breakups as well. So we were interfering with each other. And so now when we start to do a deployment, say out in the city, we have to understand how we deploy to maximise the chance that our signal gets through, knowing fine rightly that not only will other systems be out on the same channels, especially since we're using the license-free band of radio, but that we have to account for that and be able to overcome that. And so we're now starting to see bunches of low-powered wide area networks that really are really good at doing that in the electronics. So it takes into account both the noise that you would almost expect, but also the interference from these third parties. So it's things that you don't even know exist out there at the moment. So the received signal then is distorted by the channel and can be corrupted by noise and interference. So that basically has, the result on the received bits means that some of them may be missing. Now the error correcting codes on the receivers can cope with that to a certain degree, but only to a certain degree. So the MAC protocol's job is trying to maximize the data coming through. And what the MAC protocol has to do, it has to look at energy efficiency, avoid collisions, be scalable and adaptable to the changing environment, also be of low delays. It needs to be fair, in other words, it can't make certain nodes become more heavily used than others. It needs to have a decent throughput in terms of the amounts of data being sent, and utilise the bandwidth, not only for your application, but because your application is sharing the same space as another, it can't just dominate. So the sources of energy inefficiency in regarding the Mac is things like when there's a collision, you have to resend. If you're overhearing something that's not meant for you, will hear it, so you actually consume energy doing that. You may have to send housekeeping packets, which cost, and as I said before, the idle listening. At this point, how much time do I have left for this session? Whatever. Not much. Are we done? Right. So what I wanted to do is just these two protocols, and then we're finished. The first one is called the Tdma, time-based division access. And all you're doing here is I am a base station, and I've got a bunch of nodes in the space, and I say you're my nodes, and I'm the base station. I allocate you a time when you're allowed to send me stuff, and you have to stick to that time. Now that's used typically in all modern radio network control systems. So I can say, you start first, you will start, and then you get a couple of seconds or a millisecond, and then yourself, and it goes in that order, and it round robins. Yeah. Now the advantage of that is I can guarantee your slot. As long as your clocks are synchronized with mine, I can guarantee your slot, and you will send in that time. Now for certain applications, that means though that you might have had a phenomenon you wanted to report, and you've had to wait until your slot time. It also means that if something is, for example, if I've got a leak in the pipe and I'm getting lots of data I need to send, it's buffering up, and I have to wait for my send time to basically send that. So it means the round robin to your next time depends on how many nodes are in the system. So it doesn't scale well. Also, there's tricks you can do with regards to that, and that processing is NP hard, which is not easy for a small base station to process, so we have to do heuristics to make that processable and so on. So Tdma is what is used a lot in control systems. It's being used a lot in low-powered wide area IoT networks in London. They use LoRa, use N-Wave, and all those networks. You're starting to see that being used there because it's simple, but it doesn't scale very well. The alternative, if I can get this to run faster, is contention-based, where I know I need to send something now. I listen and hear the error. If nobody's transmitting, I will send. Now that's great, that works to a certain degree, but there is a problem with that. I'm talking to, say, you at the back, and I can hear nobody else talking right now, but as I start to send, you maybe can hear somebody else in the other room out there that I can't hear. So I've started to send, and somebody's already outside sending you that data, and you're going, well, I'm getting two pieces of data in here, I have a collision. I can't process this. And this is called the hidden terminal problem, where I think it's quiet between me and my receiver, but my receiver can hear somebody else I can't hear. And that's the problem with contention-based. But contention-based is fairly efficient otherwise. And we have different Macs that look into that. So we've basically synchronous Macs that everybody in the, knows when to wake up and they talk to each other. Asynchronous Macs basically are where I send I want to send preamble, I want to send, you wake up, take my stuff, send, right? So basically you're sending preamble. They've both got different trade-offs. Synchronous means I have to synchronize everything, which costs. Asynchronous means I don't have to synchronize, but I do have to send that preamble, and that costs. So there's different ways to do Macs. In terms of routing, we've talked about multi-hop routing. I'm not going into detail any further, but I'll show you CTP, because it's the one that's probably the most used, if my slides would work. Come on. Come on. Where is it? This is a trouble animation when you're trying to get through. What did I do? Right. So CTP is up the stack now. So you've got something will handle the medium for you. So when you need to use the medium to send a message, something else is doing that for you beneath you. You're just wanting to route. You're saying, okay, I'm going to send my data from A to B. I don't care about the medium. You tell me, the MAC layer tells me when I can get access to the medium. So what we have is an example of CTP, which is collection tree protocol, very, very simple. It's basically got a forwarding engine, a routing engine, and a link estimator, okay? And so what it does is, when it wants to send, it kind of understands who its neighbor is by sending out pings to each of its neighbors. Now, it doesn't send a single ping and say, right, your received single strength is brilliant, right, you're my good neighbour, and you're not so good, and you're not so good, and you're brilliant as well. It sends it out over time and averages it, because things get in the way, and it's very, so you want an average of you're a reliably good neighbour for a number of seconds, and you're an awful neighbour for lots of seconds, and that sort of thing. And it thinks, right, okay, you're an awful neighbour, you're not in my neighbour table, you're good and you're good, you're now my neighbours, and I choose between you at a moment in time. So basically that's the link estimator, and that does that very efficiently at the lowest level. So that's the ETX. In other words, it's getting a notion of quality between me and my good neighbours. And then from that ETX, I choose the best one for each of the hops. And that's how we forward our data packets. Let me see if I can show you it. It's very simple. So for example, if we've got 2 nodes, B wants to send it up the network to somewhere up here, up at the top. B will then ping here to see what its ETX is. The link between D and B is ETX of 1. The link between B and C is ETX of 3. Now the whole network accumulates these ETXs per hop along the network, and we choose the lowest one. So my ETX here is nice because this is how we calculate it. It's basically the packet receive ratio forward multiplied by it back 1 over that. And then I know the lowest ETX is my best. So if both those nodes are the same up the network, their access to the rest of the network's the same, I will choose this one. Now had this have been a really low number like 1 plus 3 is 4, then its ETX would have been smaller and I would have used that one instead. And it's a super lightweight way of basically making sure the network gets reasonably fast packets reliably up through the network, and it's such small amounts of processing to be done to achieve that. It can also do things like account for failure, where the system can route round, and if it starts to notice, for example, that there's a routing loop, it can detect those as well. So it's such a small, lightweight calculation that represents a whole network by only understanding your neighbour nodes, and you can do things like eliminate loops and everything. Okay, so it's a really nice system. It's super lightweight. So we say it detects its loop now. Yay. Yes, so it knows it's got a loop, and that's a problem. Okay. Now, the one thing that routing metrics do is that one there that I was talking about just looked at link quality. We can add other things to it, that calculation. And that calculation we call the objective function of the routing algorithm. So the objective function can take into, for example, things like the energy in the nodes. It can take into account other things. For example, maybe there's hotspots in the network. For example, that could turn into a hotspot. So you want to start routing around the less used areas to make sure that the network as a whole maintains its lifetime and so on. And we plug these into the actual system to make it run at a network level. So basically what we've looked at today in summary is we've introduced the challenges for wireless sensor network. We've looked at the MAC layer and the routing layer, and this kind of gives you a foundational understanding of the whole subject, because they are typically run, those layers are typically similar for most of the systems. So what we're looking at next, we're looking at how we can get rid of batteries and look at harvested energy and how we maximize that. We look at a little bit of signal processing. We look at security and control, and then we start to map our way back to programmable matter from there. And that's after your lunch. Thank you very much.